last lecture. Hello. So where did we stop last time? We stopped at the statement of the theorem. The varieties that we constructed of the form T of sigma are exactly all irreducible normal varieties with a torus section with an open orbit and this open orbit is isomorphic to the torus itself. And what I didn't say last time, although, well, it is not necessary for the theorem, but it is also better to mention that all these actions are so-called faithful. Which means that there are no points of the torus except one that act trivially on the whole variety. Act trivially means don't move any points. It is possible that some elements of the torus fix some points. There are also even fixed points of the whole torus, but there are no points of the torus which fix the whole variety. Any questions about the last time? Then before we proceed, so today we are going to talk about orbits and hopefully about non-affine toric varieties. But before we proceed, I want to state an important lemma or a theorem about normalization. So about normal varieties, as we said it. So for algebras, on the side of algebras, the lemma looks like this. So theorem without proof, and this is actually a complicated theorem that if we have a finitely generated C algebra without zero divisors, then all solutions in the quotient field, in the fraction field, of equations x to the n plus a n minus 1 x to the n minus 1 plus the dot plus a1 x plus a0 equals 0. Such polynomial equations with leading coefficient 1, ai in A, all solutions x from the fraction field of such equations form an integrally closed finitely generated algebra. So algebra requires a proof, but is easy. That such solutions, this set of solutions is closed under addition and multiplication. This is easy. Integrally closed is also, well, not so hard. That if you take all these solutions, then if you use them as new coefficients, nothing more will appear. But the hard part is finitely generated. This is hard, but it is true. So, and this algebra is closed. The integral closure of A. And on the geometric side, this means that if x is not necessarily normal irreducible variety, so maybe we don't have normality, but we must have irreducibility. Then y equals spectrum of this integral closure of C of x is called the normalization of x. So here we have a morphism, an embedding of the algebra into its algebraic closure. And here we have a morphism from, we have the other way around. We have a morphism from y to x. Any questions here? So, well, this is just a theorem without proof. And this, well, we don't have time to study the properties of this morphism, but it is quite close to an isomorphism, informally speaking. So, every variety can be almost isomorphically replaced to a normal variety. Every irreducible variety can be almost isomorphically replaced with a normal variety. And one more correction about the last lecture. What I was thinking about normal but not irreducible varieties, I said that they exist and the definition is complicated, so the definition which I was thinking about was wrong, although I didn't state it. But the correct definition is actually not complicated. So we say that a not necessarily irreducible variety is normal if it is a disjoint union of irreducible normal varieties. So we simply must have a disjoint union. For example, we put them into parallel hyperplanes in a space of one dimension higher. So these are non-irreducible varieties that are called normal, and The definition is not very complicated, actually. Now let us talk about orbits of the torus section. Okay, we start with a lemma about combinatorial geometry. Suppose we have a multiplicative function on the integer points of a cone. Then first the points b in tau z where f of p is not zero form a subspace H, well, intersected with tau z. So there exists a subspace such that all non-zero points are exactly the intersection of this subspace with tau z. And B this subspace cannot separate tau z into two non-empty parts, which means that H intersection tau is actually a face of tau. So this lemma we can prove. Let us prove it. If we have f of p1 not equal to 0, f of p2 not equal to 0, then f of p1 plus p2 is not 0 directly by multiplicativity. If this is, well, this is always a point of tau, and there we have a non-zero value by multiplicativity. And then f of p1 minus p2, if this is still in tau, then this must not be equal to 0, because if this were 0, then we would multiply it by f of p2, and we would get 0 here. Similarly, f of p2 minus p1 is not 0. If this is a point in tau. What else can we check if we only can add points and maybe not subtract? Is if you multiply a point by a number, by a natural number to begin with, f of a times p1 is still not 0 directly by multiplicativity. And then f of a over b times p1 is still not 0 if this is an integer point. Of course, f of 0 equals 1, which is not 0. And finally, if minus p1 is still in tau, then f of minus p1 is not 0. So whatever we can reach inside tau, we can reach by either multiplying by positive coefficients, by adding, or by subtracting, or by multiplying by negative coefficients. This is a cone and not a tau is a cone and not a subspace itself, so we have to check carefully what happens when we subtract. Because if this is not a point of tau, then if, for example, we cannot say f of minus p1 always is not 0, because minus p1 may be not in tau, and then we could not deduce this from this and this. We have to check this separately. But multiplication by positive numbers, subtraction separately, multiplication by negative numbers separately is enough. So everywhere in the subspace where we have an integer point of tau, we get a non-zero value. This proves part A, and in part B we say that if H separates P1 and P2 in tau z, well, but P1 and P2 are not in H, then there exists a linear combination of P1 and P2 with positive coefficients, with natural coefficients in tau, because they are on different sides in H, sorry, because they are different sides of H. And then we get a contradiction, because here this is not in H, so at these points we have zeros, but at this point we don't have 0. This finishes the proof of part number B. Any questions here? And then we have one more lemma from combinatorial geometry saying that if we have two such functions, that have non-zero values exactly on the same face of the cone. So when I say exactly, I mean outside this face both of them are zeros, and in this face both of them are non-zeros. And also let us denote by x and y in our variety the corresponding points. Then I claim that we can move x to y. There exists an element of the torus such that t dot x is y. So here we don't prove it very carefully like there, we just state an idea. So first we extend G mod f to the whole space, well, not to the whole space, but to all integer points in our space H intersection with a character lattice. It is possible because there we only have non-zero values. Wherever we have a value, they are all non-zero. And the function is multiplicative, so we can extend it. Second, like last time, we can choose a z basis of here. So p1 is a z basis of H intersection z to the n, and then we can check that we can extend it to a z basis of the whole z to the n. We add points one by the lemma from the last time. Pk plus 1 dot pn. And then we extend f over g. Sorry, we extend g over f. Well, it doesn't matter, but if we want this, we want to extend g over f to the whole z to the n. We say that g over f of pk plus 1 equals dot equals g over f of pn simply equals 1. Well, there are many other ways to extend it multiplicatively, but we can choose one. There are also many ways to choose a basis, but we can choose one. And so at the basis points, the new function equals 1, but otherwise somewhere outside this h may not be equal to 1, because we want multiplicativity. So the values are determined by the values inside h and at these basis points. If you chose different basis points, the function will be different. So there is no canonical one, but there is something. It exists. It's maybe not unique. It's not canonical, but we say that this function g over f it's defined on the whole lattice, so it defines a point in the torus. And we denote this point in the torus by t. And then since it is, and then this g over f on the whole tau z, this new g over f times f equals g, because in the plane h, this was how we constructed it. Outside, f is just 0 and g is just 0. So t multiplied by x is y. T action on x is y. So as a corollary, we now see that all points of the variety corresponding to multiplicative functions that have non-zero values exactly on a fixed face of tau, all these points actually form an orbit, form a single toric orbit. Well, we've just seen that all these points belong to the same orbit, but when we act by a torus, we multiply our multiplicative functions by the values of our multiplicative functions by non-zero numbers, so the phase where all non-zero values are contained cannot change when we act by a torus. So this is the whole orbit. In other words, we have a bijection between orbits and phases of tau. Any questions here? Okay, these are separate orbits, and now let us see how they are connected. So there was an open orbit. These ones are of course not open, but the question we can ask is, if we take the closure of an orbit, the minimal closed subset which contains this orbit, how does it look like? We will see that it contains some other orbits. So how can we describe such an orbit with equations? You say that this is the intersection of the closed subset defined by the equations x, the p equals 0 for p from tau z without h. Outside our phase, we have 0 values for multiplicative function, meaning these functions are all zeros. And then we intersect it with the open subset x, the p not equal to 0 for p in the phase. So from these equations, it's important that we can have finitely many of them. for example, a basis of H in tau z, not even necessarily a z basis. A z basis, no, even a q basis, if it take points from here, if we have non-zero values there, it guarantees that we have non-zero values on the whole H, because this is the smallest subspace containing all these points. When we have finitely many inequalities like this, function not equal to 0, we have an open subset, and when you have equations whatever many that some function equals 0, we have a closed subset. So let us call it y. Let us call this one z. So our orbit is the intersection of y and z. So let us look what this y is now. We see that the algebra of functions on this closed subset y is, well, outside the face we have zeros everywhere, so this is just the direct sum. This is essentially a subalgebra of our function algebra on the variety, namely we take the sum over all functions over all points in the face of c times x to p, because outside the face we just have zeros. So this algebra, as a subalgebra of the original algebra of functions on the variety, does not have zero divisors. Meaning that this y is irreducible, and z intersection y, it's an open subset of y. It's defined by these equations inside y. So it is dense in y. So the closure is exactly y. So the closure of the orbit, z, so y intersection z, closure equals y. This bar denotes the closure, which is by definition the intersection of all containing closed subsets. So from the point of view of orbits and from the point of view of multiplicative functions, we say that we have this conclusion. The closure consists of all points corresponding to the multiplicative functions where outside the face tau z intersection h we have zero values of the multiplicative function, and inside this condition is ignored because we are talking about the closure about y, not about y intersection z. So inside tau z intersection h, whatever. Maybe zeros, maybe no. So in other words, this is the union of orbits corresponding to subfaces of tau z intersection h. Some faces inside here. Orbits correspond to faces where the function, the multiplicative function, has non-zero values, and these faces, maybe it's tau z intersection h, or maybe it's a subset inside there, if here we indeed sometimes have zeros. Any questions so far before we see an example or some few examples? So the first example, we start with a cone sigma in the dual lattice of the character lattice. This will be the positive x, y values. Then, as we know, the dual cone looks the same. And we have 4 orbits corresponding to the 4 faces. So here, inside, we have a multiplicative function which has non-zero values everywhere. To guarantee this, we need to say that, so this is c of x and y. It's enough to say that x is not 0 and y is not 0. So there are 4 orbits. This orbit is the open orbit, the torus itself. Then there are 2 sides, 2 edges. And here we have x not 0, but y is 0. And here we have x is 0, but y is not 0. These are coordinate axes without 0. And finally, here we have zeros everywhere except the origin. So x equals 0, y equals 0. Well, this is the origin. And now the closures. The closure of this orbit of the torus is everything. And the closure of this orbit consists of this orbit and this orbit. And the closure of this orbit consists of this orbit itself and the last orbit, the origin. Likewise, if we start with the whole angle as the face, then the subfaces are all 4 faces. If we start with one of the sides, the subfaces will be this side and the origin. And if you have the origin, we don't have any subspaces. In the second example, our sigma again looks like this. And tau also looks the same. The variety was xz equals y squared. Again, we have 4 orbits. So this is x, this is y, this is z. We have 4 orbits. The first one is non-zero everywhere, meaning x is not zero, y is not zero, z is not zero. This is the torus. Then we can have non-zero values here, meaning z is not zero and x and y are zeros. And we can have non-zero values here, meaning x is not zero, y is zero, z is zero. Or we can have the only non-zero value at the origin, meaning x equals 0, y equals 0, z equals 0. The picture of inclusion of closures is exactly the same as here. The closure of this contains these 3, and the closure of this contains this one. The closure of this contains this one. And one more example. Let us say we have a ray inside a 2-dimensional space. This is our sigma. Then tau equals sigma check equals this half space. So the variety is a spectrum of x, y, and y inverse. X, y, and y inverse. And we have 2 orbits. Y is always non-zero because it's invertible, but there is an orbit where x is also non-zero. And this is the torus. And then x equals 0, which means a coordinate line without 0. It's a line without a point. Okay, this finishes the description of the orbits and their closures, at least in terms of the cone tau inside the character lattice. We will see soon how to describe them with the dual cone, with sigma, but for now it doesn't look very helpful. It will be helpful when we try to construct non-affine toric varieties. So, any questions so far? After that, we will start talking about non-affine varieties. Okay, if there are no questions, let us talk about non-affine varieties. So, a question for you. Do you know differential geometry? Do you know how to construct differential geometric varieties out of balls and transition functions? Out of open subsets of Rn and transition functions? No. Okay, well, I thought you would know this. We don't need this, but if you knew this, this would be a familiar picture. What we are going to do would be a familiar picture for you. Otherwise, it's not so familiar. Oh, sorry. In differential geometry, they are called manifolds, not varieties. So are you familiar with differential manifolds? No? Okay, do you know projective planes in differential geometry? Do you know how to build projective planes out of n-dimensional projective planes out of n vector spaces? Okay, well, anyway, I'll explain you the construction in algebraic geometry. I don't know how familiar it is going to be for you. But before we see that construction, we need some preparation. We need so-called rational functions. So for us, today we will only use irreducible varieties. So suppose we have an irreducible affine variety x. We say that a rational function, we say that first a rational function on x is simply an element of the fraction field. And we say that it is defined at a point x small if there exists f1 and g1 two regular functions with f over g equals f1 over g1 in the fraction field, and g1 of x is not equal to 0. So why we do this, why we say there exist f1 and g1, because we don't necessarily assume that there is unique factorization. And if there is no unique factorization, then we cannot say, like, let us simplify the fraction in the maximal possible way. We can do this with numbers, but we cannot do this if we don't have unique factorization. Here, for example, we have x over y equals y over z, and we cannot say this fraction or this fraction cannot be simplified. They are, well, equally bad or equally good. So we say there exists f1 and g1. So about these rational functions, to give some orientation, there is a theorem. Well, I'm not actually sure about the statement. Maybe it's only true for normal varieties. But we don't need this theorem, just side remark without proof. Without proof. Maybe for normal varieties only. that first a rational function is defined everywhere on X, if and only if it is regular, meaning that it can be written as some regular function f divided by 1 in the fraction field, and b defined everywhere on a principal open subset, X without v of f, if and only if it equals some g divided by f to the n, where g is something and f is this f. So in addition to regular functions, we also have rational functions. And we also have, instead of morphisms, we have so-called rational maps between affine algebraic varieties. So we have two varieties, x in Cn, y in Cm. Fine. And x also irreducible. Then by definition, we say that a rational map from x to y is simply an m tuple of fractions. f1 over g1 dot f m over gm from the field of fractions on X such that, well, let's say that the algebra of functions on Y is the polynomial algebra modulo an ideal I. Such that, and here then we say such that for every equation H from the ideal, we have H of f1 over g1 dot fm over gm. When we plug in this, we get 0 in the field of fractions. So in other words, or well, let's say first that a small example. We have a rational map from C to C itself, where the point with the coordinate x goes to the point with the coordinate 1 over x. This is of course not defined everywhere, but it is defined at all points except 0. And generally we say that a rational map is defined at a point x small if all fractions fi over gi are defined at the point x. And like with regular functions and regular maps, we see from here that rational maps are in bijection with morphisms of algebras from the regular functions on y to rational functions on x. Because just like with regular functions, if we have such an m tuple, we can send each yi to fi over gi, and then this condition guarantees that this map will not only be defined on the polynomial algebra, this one, but also on the algebra of functions on y. Then let us introduce non-affine varieties. So we say that to define a non-affine variety, we need the following things. First, a finite set of affine varieties u1 ... uk called affine charts. Affine charts. Second, in each of these affine charts, we choose. So today for us, well, in general it's not necessary, but today for us it's better to have them irreducible. Then in each ui, we choose an open, we choose open subsets uij for all j from 1 to k, but not I. So these uij's in ui will be glued with uji in uj, will be identified with uji in uj. And to do this, for each pair ij, I not equal to j, we have rational maps. Fij from ui to uj, yeah, rational maps are defined with this, are usually denoted with these dashed arrows. And fji from uj to ui. So Fij must be defined on the whole everywhere on uij. Fij of x must be in uji if x is in uij then if we apply first Fij to x and then Fji to the result, we get x back and the symmetric condition for Fji and one more condition, kind of looking like equivalence conditions, like transitivity in the definition of an equivalence condition. Namely, if x is in uij, then these two conditions must be equivalent. X is in uik if and only if Fij of x is in ujk. So meaning that if we can send it, if we can send x from I to j, and we also allow to send x to another set k, to another affine chart k, then we must be able to send it first to j and then from j to k. And if these hold, if these two conditions hold, then Fik of x, when we send x directly to k, is the same thing as when we first send x to j and then send it to k. These Fijs are called, these rational maps Fij are called transition maps. And then we say that we identify each x in ui with Fij of x for all j such that x is in uij. And we also identify each uij with uji. So this way we have sort of contracted our set of points. Originally we had these separate sets, and now we identified some points. And we say that all these points together, after this identification, form a non-affine algebraic variety. Okay, so I think it's time to make a break. So after the break, we will start with some examples of non-affine algebraic varieties.